So this is the lecture 2 of processor logic design. In almost all the CPU, okay, there is a register called status register. Okay, it is sometimes convenient to supplement the arithmetic logic unit with a status register, where the status bit, for example, overflow bit. Suppose you are doing some addition and there is an overflow. Okay, so this overflow bit will indicate the situation that there is an overflow happened. So by checking the overflow bit, we can tell that okay, there is an overflow. Let's say zero indication. Suppose you have done the addition or subtraction and the result is 0. So by checking the 0 bit, we can tell that okay, the result is 0. Sign bit. Suppose you have done addition or subtraction, your number is negative. So how you can understand the number is negative? By checking the sign bit. Okay. So this status register is very important. Almost in all the CPU you will find a register called status register or flag register. And this flag register stores conditions of different operation of the CPU. Status bit conditions are sometimes called condition code bits or flag bits. So this is a sample status register for the 8-bit ALU of our model arithmetic logic unit system. If you look at the picture, this is the status register and it has 4 flag bit. This is the overflow bit. Okay, this is the 0 bit Z. Third bit is the sign bit and first one is carry bit. Okay, so this is a sample status register implementation for your arithmetic logic unit that we are covering in this chapter. So figure 914 shows the block diagram of an 8-bit ALU with a 4-bit status register. The 4 status bits are symbolized by C, S, Z and B. The bits are set or cleared as a result of an operation performed in the arithmetic logic unit. Bit C is set if the output carry of the ALU is 1. It is cleared if the output carry is 0. Bit S is set if the highest order bit of the result in the output of the ALU, that means the sign bit, is 1. If you see that okay, S bit is 1, that means your number is negative. Okay, and if you see that okay, this bit, this is usually the MSB. Okay, it is 0, that means number is positive. So this is clear if the highest order bit is 0, that means number is positive. The bit Z, okay, is set if the output of the ALU contains all zeros. Suppose you have doing some arithmetic operation or logic operation, but the result is 0. In that case, this Z bit will be set to 1. And if the result is non-zero, then Z bit will be set to 0. The overflow bit V is set if the exclusive OR of carry C8 and C9 is 1. This is the condition for overflow when the numbers are in science 2's complementary representation. For the 8-bit ALU, V is set if the result is greater than 127 or less than minus 128. Basically, this overflow bit is set to 1 if there is an overflow. Okay, that means the operation where arithmetic or logic operation you are doing, usually okay, the arithmetic operation you are doing, if the result does not fit within the register, the result you are getting, it does not fit. That means it needs more space. Okay, but it cannot accommodate all the result. In that case, a situation called overflow. Then this V bit is set to 1. Otherwise, it is 0. So status bit after subtraction of unsigned numbers A minus B. So a particular example has been shown over here. If you are doing some subtraction of unsigned number, depending on the relation, if A greater than B, then this will be the condition of a status bit, and this is the Boolean function. Okay, a particular situation has been analyzed over here. If A greater than or equal to B, then condition C will be 1, and this is a Boolean function for you. If A less than B, then C will be 0. This is a Boolean function, C bar. Okay. If A less than or equal to B, then these are the bit condition, flag bit condition. Okay, and this is the function. So it is a particular example. Depending on the situation, depending on the operation, different bits will be set or reset to 0. That's the basic concept. Okay. Depending on the LU operation, this bit will be set or reset to 0 to indicate the status of the operation. So you can use this information to carry out further action. Okay. So next important part we are going to discuss shifter. Shifter is used in your processor logic design or inside the CPU to shift the output of some operation to the bus system. Okay. Suppose you are doing the addition operation A plus B. Okay. The result, how you will shift the result to the output bus? How will shift the result to the destination? So this is the job of the shifter. Look at over here. The shifter unit attached to the processor transfers the output of the ALU onto the output bus. The shifter may transfer the information directly without a shift, or it may shift the information to the left or right. Provision is sometimes made for no transfer from the ALU to the output bus. The shifter provides the shift micro operations commonly not available in the ALU. Usually, inside the ALU, when you implement, usually they don't implement the shifter inside the ALU first in some situation. Okay, not all the cases. Sometimes you can implement the shifter inside the ALU, but sometimes you may not. So when the shifter is not inside the CPU, okay, they need to design it separately. So the shifters provide the shift microoperations commonly not available in the ALU. Inside the ALU, there is no shifter. So shifter will be the outside of the ALU. Okay, but inside the CPU. Make sure shifter will be on the outside of the ALU, but inside the CPU. Yes, circuit for a shifter is a bidirectional shift register with parallel load. So in our chapter on this example design, we'll use a bidirectional shift register with parallel load. The information from the ALU can be transferred to the register in parallel, either shifted to the left or right. In this configuration, a clock pulse is needed for transfer to the shift register, and another pulse is needed for the shift. One more pulse is needed for transferring the information from the shift register to the destination register. So this is our shifter. Look at the picture. The transfer from the source register to destination register can be done with one. Yes. The transfer from a source register to destination register can be done with one clock pulse if the shifter is implemented with a combinational circuit. In a combinational logic shifter, the signals from the ALU to the output bus propagate through gates without the need for clock pulse. Hence, only one clock pulse is needed. A combinational logic shifter constructed with multiplexer are shown below. Look at over here. In this case, there are 4 multiplexers. 1, 2, 3, 4. So, every multiplexer is for a single bit. Right? So, it is a 4-bit shifter. Bit F1, F2, F3 and F4. If you want to design a shifter for 8-bit, then there will be 8 multiplexers. Okay, so this is a 4-bit shifter. Now look at over here. How you shift the result? Let's say this is the result, F1 to F4, 4-bit result from your ALU operation. And you want to shift this result to the output bus. In this case, if we use the 2 selection variable S0 and S1, look at over here, S0 and S1. With 2 selection variable, 4 ways we can shift. Okay, 4 ways we can shift. If the selection variable is 0, 0, then transfer F to S. That means the result is directly shift to the output bus. No shifting. That means whatever is the result, just directly shift to the output bus. No shift. It is called no shifting. Okay. If the selection bit H raised 1, they are 0, 1. Shift right F into S. Shift right. Okay, F into S. How you do shift right and shift left, I will explain with an example. Okay. If this selection bit H raised 1, they are 0, 1, then shift left F into S. Okay, like for example, this bit shift right. When you do shift right, IR, look at over here. When you do shift right, then this bit you can insert over here. A bit you can insert over here to shift to the right. Let's say 0 bit or 1 bit. Okay, whatever you want. You can use the bit external bit to shift. If you use shift left, then you can insert a bit on the IL. Okay, and if the selection pin is 0, 1, 1, 1, 1, 1, then transfer 0. Look at over here. This 0 will send to the output. So 4 ways. Let me summarize. First thing is this selection pin there 0, 0. Just simply shift this result to the output buses. Okay. If the selection pin is 1, 0, then shift right. So how do you shift right? By inserting, you can insert a bit over here and you can shift it to the right side, one by one. Okay. For shift left, you insert the bit in IL. So this third way. When the selection pin is 1, 1, this is the fourth way. You just simply send 0 to the output. Input IR. Look at this input IR and IL serve as serial inputs for the last and first stages during the shift right or shift left respectively. So I will play a short video to demonstrate how you can use this capability, what function you can implement, okay, by using shift left and shift right.
So this video is about left and right shift. This gets to multiply or divide by 2. You can also multiply by 4, divide by 4.
So look at over here. We want to see the application of shift left and shift right. So what we see over here, we are doing some arithmetic operation. X divided by 2. Okay. For example, if x equal to 4 divided by 4. Okay. So what happens?
So this video is about left and right shift. This gets used in computers to multiply or divide by 2. You can also multiply by 4, divide by 4. You can also multiply by 8, 16, 32, 64, and so on and so on. So if any one of those column headings that we have in binary, then we can multiply or divide. Let me show you what I mean. So we'll take a really simple left shift. So I'm going to put in my column headings 1, 2, 4, 8, like this. Now if I have the binary number 0, 0, 1, 1, like this, we've got 1, 1, 1, 2, add it up, and that is equal to 3. When we left shift, all we do is we shift each binary digit one place left and put a 0 at the beginning. So 0, the 1 comes across here, the 1 comes across here, and the 0 comes across here. We've only got 4 bits, so we're going to forget about that one. Now, what we can see if we add this up is 4 plus 2 is equal to 6. So, we've doubled. Now we could do this again, and we left shift the bits again, like this, and we come up with 1, 1, 0, and then we fill in the 0 because we've got nothing to shift. And that is equal to 12. So we can see that this will happen with any number. Just go through one more quick example here. So let's take 0, 1, 0, 1. So this is equal to 5. So hopefully, when we left shift, it's equal to 10. So we're going to left shift, so 1, 0, 1, and then put in the 0, because we haven't got one. And that is equal to 10. This works absolutely simply. It's as easy as it looks. So how do we divide? Well, we do exactly the reverse process. So if I have 1, 0, 1, 0, like this, so 8 plus 2 equals 10. So we right shift, we take each bit to the right. And what we end up with, we've got nothing here, because we can't shift in because we've only got 4 bits. And then we've got 1, 0, 1. And that is equal to 5. Now, there's a slight problem when we want to right shift again. What happens is we shift them over and end up with 0, 0, 1, 0. That equals 2. Now, this is a problem. This is a problem because we are dividing 5 by 2 and getting 2. But actually, that little 1 that slipped over, that's what we usually call in maths a remainder. So we can actually detect that that bit is being lost, and then we can put in a remainder. You can do this with decimal numbers in binary, but that's something we're going to leave for another time.
So what we have seen, the use of shifter. You can do multiply and divide by just simply shifting the bit left or right? So this is the function table for shifter. Okay. For operation we have seen. For conditions for control bit AGN is on 0, 0, 0, 1, 1, 0, and 1, 1. To add more operations in the shifter, 8 into x multiplication are needed with a third selection variable s2. Suppose you want to increase the capability of the shifter. Till now we have seen 4 ways to shift. If you want to do more functionality, use more selection bit. Let's say add a third selection bit h2 for the shifter. So for 3 selection bit, you can perform 8 different shifting operation. Okay. For example, circulate left with carry CLC. Okay. Circulate CLCR. Circulate right with carry. Okay. If CLCL and CLCR is used, then IL and IR must be connected to the carry bit. For example, CSR means circulate left with carry, CRR means circulate right with carry. It has some application. When you design the LU, when you do the circulate left and right with the carry bit, then we'll see On our next week, at the end, okay, when we design the control unit for the LU, it has some application. Okay, let's see an example how it is used. So in this example, look at over here. We are circulating right. Okay, 8-bit rotate right with carry. Look at over here the sequence of operation. We are circulating the 8-bit through the carry bit. So loop is completed. Okay, over here. Commence rotate right. So basically, what is happening over here? When you do the shifting, you see, by checking the carry bit, we can detect whether that bit is 1 or 0. Okay, you are shifting through the carry bit. Okay, so you have the chance to check the bit. Okay, whether that bit is 1 or 0. So depending on the finding, you can take some action. So this is the rotate right with carry. Similarly, you can do the rotate left with carry. Okay, depending on your need. So what you have seen till now, you have seen two particular part of the ALU design, processor logic design. One is the status register or flag register, other is the shifter. Now we are going to see how the entire operation gets performed by the control unit. Okay, control unit generates the control signal to perform the operation. So to visualize the activity inside the CPU, we are going to use a model system. Look at over here. This is our model system. In this model system, what we have the LU. This is 4-bit LU, right? Or 8-bit LU. I think this is the 8-bit LU we have covered so far. Okay. This is mood select pin number ST is the mood select pin. Then pin number S0S1, they are the function select pin, and this is the carry in pin. By using this ALU, we can perform 8 different arithmetic operation and 4 different logic operation. The design of this ALU we have seen in our last class. Okay. Now we'll see the complete picture. How it get performed inside the CPU. The entire picture. Okay. So we have this design this ALU. Now there are, look at over here, there are 7 register over here. Register R1 to R7 inside this unit. 7 register. Okay. This is the bus select multiplier. This multiplier is for bus select. Okay. This multiplier is for the bus B select. Means you read the word A from this register by using this multiplier. You read the word B from this 7 register by using this second multiplier, bus B select. This is a bus organization architecture. Now look at the multiplexer. There are 3 selection pin. Why 3 selection pin? Because there are 7 resistors. 2 to the power 3 is 8. That means 1 out of 8 location you can select. So that's why they have 3 selection pin. 3 selection pin for this multiplexer. So that you can select 1 out of 7 resistors from here. Similar way, bus B select multiplexer has 3 selection pin. 4, 5, 6. By using this 3 selection pin, you can select 1 out of 7 resistors from here. Yes? Yes. For every multiplexer, you have separate selection pin. Why? Because control unit need to distinguish the selection pin from the selection pin. Yes, look at over here. This is the, it will be more clear if you analyze this control watt. Control unit will generate the control watt with every clock cycle. Look at over here. This is A. Look at over A. It has 3 bit. So control watt will have these 3 bit over here so that you can select your register of choice. Okay. Similar way, this B inside the control watt, B is also 3 bit long, 4, 5, 6. So this B will have this particular 3 bit so that you can select a particular register. So you will supply this control bit over here depending on your requirement. If you want to, let's say, for example, select register R7, you write 1, 1, 1. Suppose you want to select the register, let's say R1, 0, 0, 1. Okay. So depending on your requirement, you will supply the control one. Accordingly, this will come over here. Look at the 1, 2, 3 for A. 4, 5, 6 is for B. So if you specify the proper control bit over here, accordingly, that particular register will get selected for bus A select and for bus B select. Yes, 3 pin over here because we have 7 register. If you have only 4 register, then also only 2 bit unit. If you have, let's say, 16 register, then you need 4 bit for that situation. Okay, so depending on the number of register, you need the number of bit. It depends on the design, how small and how big your system is. In this case, our register is only 7 register. If you have 7 register, then you need 3 bit. 0, 0, 0 for one register, for example. 0, 0, 1 for another register. 0, 1, 0 for another register. 0, 1, 1 for another register. 1, 1, 1 for another register. So 3 bit for a particular location. Okay, 3 bit for a particular location. If you have 16 register, then 0, 0, 0, 0 for the first register. 0, 0, 0, 1 for the second register. Okay, so depending on the number of register, you need to use more or less selection bit. Okay, so this is the bus A select, bus B select bit. Look at over here, D for the destination. After you perform the operation by the ALU, at what destination register you are going to store the result. So that is defined by the destination select D. You see, look at over here. This is the destination select D. Bit position 7, 8, and 9 for your control word. 7, 8, and 9. Okay. Bit position 7, 8, and 9 for your control word. Okay. Bit position 7, 8, and 9 for the destination. Look at over here. Your destination select. So by using this 3 bit, you can specify at what register the result will get stored. Okay. Next, look at the control one, the function bit 10, 11, and 12. 10, 11, and 12. What operation you are going to perform? In our last class, we have seen 8 arithmetic operation and 4 logic operation. So by using these 3 bit, you can specify what particular operation you are going to perform by bit position 10, 11, and 12. 10, 11, and 12. This 3 bit. Okay. carry in bit. This bit then is specified whether it will be 0 or 1 depending on your requirement. Okay. For arithmetic operation, carry in bit has the meaning. For logic operation, this is meaningless. For logic operation, you don't use the carry in. Don't care. Okay. Now, this 3-bit position 14, 15, and 16. 14, 15, and 16 for the shifter. How you'll shift the result from the LU to the output box. If you want to directly shift the result without any change, that means 0, 0, no shifting. 1, 0, 0, 0, 0, no shifting. Look at the function table. Look at over here. When this 3-bit are 0, 0, no shift. Just send the output result to the output bus. When that 3-bit is 0, 0, 1, then shift right. And we have seen the application of shift right, right? You can do multiply or divide. When they are 0, 1, 0, shift left. When they are 0, 1, 1, send 0 to the output box. When they are, let's say, 1, 0, 1, circulate right with carry. When they are 1, 1, 0, circulate left with carry. So this is the use of shifter. Now over here, look at over here. By using these 3-bit 14, 15, and 16, you specify how to shift the result to the output bus. So what we see over here? If you write a control word like this and output this control word, and with this control word we can control the operation of the entire CPU. Suppose you want to perform the A plus B. Just properly write the control word and output the control word in the system bus, A plus B will get performed with a single clock pulse. So what you need to do? You need to know how to write this control word. When you write a program, basically you give instruction to the CPU to write the control word for you. Okay. When you write the program for the computer, basically you instruct the CPU to generate the control word for you. So how your CPU does it? So we'll see with some example. So look at over here. Examples of micro operation. What are the micro operation? When you write a program, okay, your program get divided into a smaller basic operation. Each operation is called micro operation. This micro operation should be performed by your processor or CPU directly. Means that your CPU must have direct or proper hardware to perform those micro operations. So what it implies? It implies that you need to design those hardware inside your CPU. For every micro operation inside your CPU, there will be a direct hardware implementation for it. So your micro operation tells the hardware design of your CPU. Okay, your micro operation tells the hardware design of your CPU. So when you write a program, your program get converted to micro operation, and this micro operation get performed through the hardware and control signal. Control signal get generated by the control unit. It goes to different part of the hardware. That particular operation get performed. In this way, your entire program get executed. So to understand the hardware design of your CPU, it is very important to understand how this micro operation get implemented inside your CPU. So this is a particular set of example over here. Look at over here. This is your ALU design. 8 arithmetic operation. Look at over here. 8 arithmetic operation and 4 logic operation. This is the binary code control bit for the arithmetic and logic operation. This is a summary from your last lecture. The ALU can perform 8 arithmetic operation, and this is the arithmetic operation 4. Okay, this 4 arithmetic operation, another 4 arithmetic operation, means in total 8 arithmetic operation, depending on carry in equal to 0 and carry in equal to 1. When the carry in equal to 0, 4 arithmetic operation you can perform this 4. When carry in equal to 1, this 4 arithmetic operation can perform. When you perform logic operation, that means if the mode select pin is 1, only logic operation will get performed. This 4 logic operation can get performed. So what we see over here, this is the summary of the ALU, okay? ALU table that we have done in our last lecture. 8 arithmetic operation and 4 logic operation. And this is the table for the shifter. Okay? Table for the shifter, depending on the selection pin or selection bit. Depending on the selection bit, and this is the selection bit for different register. Word A and word B. This is the destination. This is the carry in. This is the edge. Okay. So from this, excuse me. So this table will be used to write the control word. For example, this is our first micro-operation. R1 minus R2. We are performing subtraction operation R1 minus R2, and the result will get stored in the register R1. So for this particular operation, look at over here. For this particular operation, what will be the control word? So first thing, if you look at over here, this is the control word. So what is word A? Word A will select the these 3 selection pin 1, 2, 3 will select the word A, right? We select the word A. So in our case, what is word A? Word A is R1. So what selection between it? For R1, look at over here. For R1, our selection bit is 0, 0, 1. So we write 0, 0, 1. Now look at over for word B. Bit position 4, 5, and 6. So what is word B over here? R2. So what is the selection pin for R2? 0, 1, 0. So this is 0, 1, 0. What is the destination? Our destination is R1. Right? Our destination is R1. So what is the binary code selection pin for R1? 0, 0, 1. So you write 0, 0, 1 over here for the D. For the D, 0, 0, 1. What is the function we are going to perform? We are going to perform subtraction operation. R1 minus R2. So what is the subtraction operation? Look at over here. When A minus B, look at over here. Carry in equal to 1. When carry in equal to 1 and your function code is selection code is 0, 1, 0. You see 0, 1, 0, and you are performing A minus B when carry in equal to 1. Okay, so carry in equal to 1 and your function code is 0, 1, 0. Okay, so it will perform subtraction operation. After the subtraction operation, how will shift the result to the output bus? You see, no shifting means you directly send the result to the output bus. You not shift left or shift right. Directly send the result to the output bus. For no shift, your selection bit is 0, 0, 0. So it is 0, 0, 0. So this is the entire control word for the micro-operation R1 minus R2, and the result will get stored in R1. So what your CPU will do? Your CPU will output this word. Okay, your CPU will output this word on the bus system, and this A minus B will get performed and the result will get stored in register R1. So this is the way inside your CPU operation get performed. Control unit generate this control word for this particular microoperation and operation get performed. Simply like this. So when you design the processor unit or CPU, you need to find out how many microoperation you are going to implement for your system. It defines the ability of the CPU. You have more microoperation, more high-level instruction you can write, or more instruction you can write. Okay. If you have less microoperation, less number of instruction you can implement. So it defines the capability of your CPU. How many microoperation your CPU can perform? That means how many hardware implementation are what there for the microoperation. If you have more microoperation, then more hardware will be required. Cost will go high. If your CPU can perform less microoperation, less hardware will be required, cost will go low. So this number of microoperation that is supported by your design determines the capability and cost of your CPU. Okay, we'll see another example. R3 minus R4. Similar way, you see. In this case, you are performing the subtraction but not storing the result somewhere. For example, when you do the compare operation, A greater than B, A less than B, or they are equal. When you do the compare operation, actually you do the subtraction, but you don't store the result in that case. Okay. Usually instead of the CPU, compare operation is done by subtraction, but you don't store the result. So this particular microoperation will do the subtraction. It will only affect the flag register. So by checking the flag bit, you can tell whether A greater than B or A less than B or they are equal or not. Okay. So how this subtraction operation get performed? Look at over here. For the control word A, you need to select R3. How to select R3? Look at over here. 0, 1, 1 for R3. 0, 1, 1 for R3. So this is 0, 1, 1. 0, 1, 1 for R3. Okay. What is R4? Look at R4. 1, 0, 0. 1, 0, 0 for R4. What is the destination? No destination. Okay. No destination. Look at over here. None. Destination is none. And the control bit for none is 0, 0, 0. So this 0, 0, 0. What is the function? Subtraction operation. A minus B. For this subtraction operation, your control bit should be 0, 1, 0. And the carrying bit should be 1. So this is the 0, 1, 0. And this is 1. Okay. And how it is shifting? No shift. Okay, no shift. Because you are not shifting a bit to the left, you are not shifting a bit to the right, you are not doing the, let's say, circulate left with carry, circulate right with carry, you are not shifting the 0 result to the output bus. If you look at the function table, these are the operations you can do perform the shift. Shift right, shift left, 0 to the output bus, circulate right with carry, circulate left with carry. And your operation does not fall within this one. What is left? No shift. So that's your choice selection. Okay, there is no shifting you are doing over here. So you just select 0, 0, 0 for the shift operation. So actually it is the compare operation. What it will do? It will only affect the flag register. Let's say if R3 and R4 they are equal, your result of subtraction will be 0. When the result of subtraction is 0, what flag bit it will affect? Z bit. 0 bit. Z bit, okay? The Z bit will be set to 1. So when you will check the Z bit, and if we find that, okay, this is 1, then you know that subtraction result was 0, that means they are equal. Numbers R3 and R4, they are equal. Now, if yours, let's say R3 is greater than R4, R3 is greater than R4, then the subtraction result will be positive number, right? So the sign bit will be 0 because number is positive. So by checking the sign bit, you can tell that, okay, sign bit 0. So R3 was greater than R4. You can find the result. Now, if R3 is less than R4, then result will be negative, right? When the result is negative, then sign bit will be set to 1. So by checking the sign bit, you can tell that, okay, sign bit is 1. So R3 was greater than R4 was greater than R3. Okay, R3 was less than R4. Okay, because a negative result. And by checking the sign bit, you can tell that. So this is used for compare operation, greater than, less than, or equal. You do the subtraction, but you don't store the result. Okay. Next, let's say just move operation. From register R4, you'll move the data to the register R5. Okay. Just move operation. Move from one location to another location. Move from one register to another register. This is called move operation. Okay. So how you perform it? Look at over here. Your destination is R5. So what is the selection pin for R5? Look at over here. 1, 0, 1. For R5, 1, 0, 1. So, okay. Register R4 is going to R5. Okay. So R5 is the destination. 101 is the destination. Look at over here. This is the destination. Okay. This is the destination. It is going to R5. So D will be 101. And A and B, both same. A and B, both same over here. No difference because this is only R4. So A and B will be this. A is look at over here. This is A and no B over here. So A is R4. So what is R4? 100. 100. And there's no B. Actually, there's no B. Only A, right? No B. So this will be 000. None. Input data 000. No B. Okay. So it is 000. Only one register R4. So what do we see over here? This is R4. A. B is 0. Destination is R5. And what arithmetic operation? Look at over here. Function. Transfer operation. Okay. We are doing transfer operation. So what is the code for transfer operation? 0, 0, 0. And carry in equal to 0. So 0, 0, 0, carry in equal to 0. Transfer R4 to R5. This is transfer operation. Okay. So this is a control word for the transfer operation or move operation. Next, another example. Input. We'll input some data to the register R6. So let's say from keyboard or from some other source. So how to do it? R6 is the destination. So look at over here. Destination is R6, 110. R6, 110. That's the destination. Okay, 110. R6 is the destination. This is R6. And there is no A and B input. So what is the code for input? 0, 0, 0. Input data. Okay, so we write 0, 0, 0 in both situations. You can either input A or input B. From any source you can input. Okay, so this is the destination. And what is the function over here? Look at over here. Transfer operation, right? We are just transferring the input data to the destination. Transfer operation. So function code is 0, 0, 0, and the carry in equal to 0. Transfer operation. Okay. And shift, that means no shifting. Shift control bit is 0. So input data to register R6. So this is the control word for input data to register R6. From R7 you want to output. Okay. From R7 you want to output. So what is the R7? R7 control bit is 1, 1, 1. So this R7. R7. Control word is 111. So this 111. Okay. There is no B. Okay, only one data. So you can write 0, 0, 0 over here. And what is the destination? R7 to output. 0, 0, 0. That's the destination. Destination is D. None. Because you are outputting. You are not defining the destination over here. Now, your system will take care, okay? At what location data will go. So it is you are just outputting over here. So destination is none. And what is the control bit? 0, 0, 0. So this is the destination. No shifting. And carry certainly for this one, carry in equal to I think 0. Okay. Carry in equal to in right can write 0. Okay, carry in equal to 0. Okay. Just simply transferring. Okay, just simply transferring to the output. So carry equal to 0. And no shifting. So this is the control word to output from a register. Now, for this operation, clear carry bit C. Clear carry bit C. If you want to clear the carry bit, how you can clear it? Okay. How you can clear the carry bit? Okay. If we want to place the contents of a register into the shifter without changing the carry bit, we can use the OR logic operation with the same register selected for both ALU input and. So how do you clear the carry bit? Look at over here. What operation you are doing? 0, 0, 0, 1. 0, 0, 1. Okay. Function is 000. Carry bit is equal to 0. So what you are doing? You are performing let's say R1 to R2. So this is R1 is 0, 0, 1. This is B is 0. This is the destination. And what you are doing? You are transferring. It is a transfer operation. So this is the scenario over here. We want to move or transfer data from register R1 to R1 and we'll clear the carry bit. Okay. So what is the source? R1. What is the control bit for R1? 0, 0, 1. Look at over here. 0, 0, 1. There is no R2 or B. So it is 000. What is destination? Destination is R1. So control bit is 0, 0, 1. Okay. And what is the function? Look at over here. Function is 000. function is 000. It is a transfer operation, and you send 0 to the carry bit. It is a transfer operation, and you send 0 to the carry bit. So your control bit is 000. F is 000. Function code 000. And certainly for this operation, carry equal to 0. And what is the shift operation? No shifting. 000. Okay. So clear carry bit C and transfer or move R1 to R1. Okay. Next operation, shift left R3 to R3. Okay. Shift left R3 to R3. So what is code for R3? 011. 011. What is destination? 011. Now, when you do shift, look at over here. If you want to place the contents of register into the shifter, okay, without changing the carry bit, we can use the all logic operation with the same register selected for both LU, A and B. So what is the technique over here? We'll use the all logic operation. If you want to place the contents of a register into the shifter without changing the carry bit, okay, without changing the carry bit, then we can use the all logic operation with the same shifter selected for both LU input A and B. So what we are going to do, same input will take R3 for A, R3 for B, and we are using the all logic operation. So what is the function? Destination is R3 certainly over here, 011, and this is the code for all logic operation. Look at over here, 100, 100. This is the code for all logic operation, or A or B. Okay. And what is the carry in over here for this? Carry equal to 0. Carry in equal to 0. And what is the shift left R3 with IL equal to 0? What is the code for it? Shift left. Okay. This is the code. 1. Okay. Shift left. Okay. Shift left. The code for shift left is 010. Look at over here. 010. Shift left. IL equal to 0. Okay. 010. Circulate. Okay, circulate through the R1. Circulate through R1. Circulate right R1 with carry. Circulate right R1 with carry. Same procedure, okay. Over here, we perform the all logic operation. Source A and B both are same, R1, R1. R1 is the destination. This is the logic operation. For all logic operation, carry equal to 0. And 101. Look at over here. Circulate right with carry. 101. Circulate right with carry. Circulate right with carry. Circulate right with carry. Okay. The code for it is 1. Okay. 101. The code for it is 101. 101. Okay. Next, send 0 to register R2. So R2 is the destination, 010. That's the destination, R2. R2 010 R2. And we are sending 0. That means both A and B and 0. 0 to the output bus. Look at over how we send 0 to the output bus. Look at over this operation. 0 to the output bus. Shift operation code will be 011. 011. And carry in actually 0 there. Okay. Can just simply put 0 over there. Zero to the output bus. Look at over here. 0 to the output bus. 0, 1, 1. You send 0 to the output bus, okay? So 0, 1, 1 is the shifting code. So you send 0 to the output bus. This is a destination. Okay. We are just particularly interested over here, okay? The destination is 0, 1, 0, and this is the shift operation 0, 1, 1. Otherwise, these are just simply put 0 over in other place. They are not useful for here, okay? So this will do or clear the register output. Any question over here? So this is the way you write the control word for different micro operation. Your control unit will simply output this control word to perform that micro operation. For every micro operation, there must be direct hardware implementation. So this micro operation is a picture of the hardware of your CPU. How many micro operation you have? That defines the capability of the CPU. If you have more micro operation, then more operation you can perform. So the design or size of your CPU will be larger, more hardware. So this gives you the idea of the hardware design of your CPU. You can get a picture of your hardware design from the micro operation. And this is the basic operation performed by your CPU. By combining several micro operation, you can define a particular instruction. Okay, you can define, like you can combine several micro operation together to define a particular instruction. So with this lecture, you have found the idea how micro operation get performed and implemented inside your CPU. So that's the end of the lecture for today.